Now, what we're going to do is we're going to start with the rules for assigning an oxidation number, okay? So these are the things that you must have memorized to determine the oxidation number of a particular element and compounds. So the first rule is that all elements in their free state. So by free state, it means that they're not bound to anything. So like O2, for example, is bound to another oxygen. So remembering from 2 videos back when we were talking about polarity and dipoles, there's no overly, there's no uneven movement of electrons there. So if you've got anything that is by itself or bound to itself, its oxidation number is 0. The next one is hydrogen is +1. Now this is an important one to memorize, okay? Hydrogen is always +1 with the exception of metal hydrides, okay? So this is a metal bound to a hydrogen, in which case it's -1. However, it's not very often that we see metal hydrides. The next thing too is oxygen is -2. Now, again, there is an exception, with the exception of a peroxide, which is H2O2, or oxygen difluoride, which is OF2. These are the only 2 compounds where this exception is seen. And again, it's quite rare that we see these in a redox reaction. So these 2 charges must be memorized. They're very, very important. The next one is the metallic element in an ionic compound has the positive oxidation number. So this is a big one. It's being able to identify in a compound which of the elements are positive, which of the elements are negative. So if you see a metallic element in an ionic compound, it is the metallic element that is positively charged. The next one is in a covalent compound, so not ionic, if it's covalent, the negative oxidation number is assigned to the most electronegative atom. So it's a bit of a survival of the fittest sort of thing. So the element that is the most electronegative will have the negative charge, whereas the element that isn't as electronegative will gain a positive charge. So this is why the oxygen difluoride, there is an exception there. So yes, oxygen and fluoride are bound together, but the fluoride is negative because it is stealing those electrons from oxygen. So it's, well, not formally stealing, but it's how we were talking about our polarity. And that is why this exception exists, because of this rule here. Now the last one, and this one again is very important in that the algebraic sum of the oxidation numbers. So if you add all the oxidation numbers up for a compound, they will always equal the charge of a compound. Always, okay? And that's a big one, and we're going to use this rule here to make sure that we get our answer correct. Okay, so now that we've discussed a bit of rules of oxidation number, let's go through an oxidation reduction reaction and see if we can get it right and implore some of these rules. But I'm going to show you step by step each of the steps you need to do for all of your redox equations. Now, the first step is we need to check to see if there is a change in the charge with an element. So again, this is how you separate balancing a normal chemical equation and redox, is to look and see if the charges change. So we can see here we've got Fe2+ or iron 2+, but over here we have iron 3+. So the charge has changed from +2 to +3. So that tells me that this is a redox reaction. Now we break the reaction down into its half reaction. So there's a technique to do this, okay, is you draw little arrows like thus. So this one is a bit of an easy one because we can see iron 2+ and iron 3+, so it's by itself. So you sort of just draw a little line and connect them together. So then you draw these reactions out separately, like so. Now these reactions here, these are called the half reactions, okay? Because it's half of it. Both of them combined tell the full story. But the way that you break them down into their half reactions is that one reaction must be oxidized and one reaction must be reduced, because that it's like when we were talking about our oxidative agent or reducing agent. One cannot be done without the other. You cannot have just something being oxidized without something also being reduced, because again, this is where our law of conservation of energy comes into play. So we need to make sure that everything equals out. So if we have a look at our iron over here, so we've got iron 2 plus to iron 3 plus. So we look at the differences here. So iron 2 plus to iron 3 plus. So what is happening to iron? The answer is because that charge is increasing, remember oil rig, because the charge is going up and electrons are negative, it's being oxidized. It's losing electrons because this charge is going up. We can say that one is being oxidized. Now, let us look at manganese and oxygen with manganese by itself. So this is where things get a little bit tricky, and this is where students get very, very confused, is what they will do, and now this is the incorrect way, is they will go, okay, so we've got manganese oxide here, so that's -1, and then we've got manganese over here, and that's +2. So that means that because it's a -1 and it's going to +2, that must be oxidized. And that is incorrect, because first of all, you can't have two things being oxidized, because where are those electrons going? And secondly, the big difference here is that we're not getting an accurate charge from this compound here because the oxygens are in the way. See, there are no oxygens over here. So what we do is we need to compare the charge of the same thing. So here we're comparing iron with iron, so that's fine. But over here, we're comparing manganese oxide to manganese. They're not the same thing. So what we need to do is we need to use oxidation numbers to determine the individual charge of these elements. So remembering on our previous slide that we were looking at, that the charge of oxygen is -2. Now we have 4 oxygens down here. So we know that the overall charge of these 4 oxygens are -8. Because if each individual oxygen is -2, and there's 4 oxygens here, it must be -8 overall. Now remembering our very last rule on the previous slide, and that was that all the oxidation numbers must add up to equal the overall charge. So we can see here that this is -8. So if the overall charge of manganese and 4 oxygens is -1, what must the oxidation number of manganese be? Now the answer to that is +7. Now I can almost hear people yelling through the YouTube screen saying, but wait a second, bro, how can you say that? You know, you've spent so many videos telling us that, you know, manganese would only have 2 electrons in its outermost shell, and that the D shell doesn't count. What's going on? How can there be 7 electrons to be stolen? And my response to that is, it is because these oxygens are so electronegative that not only did it strip the valence electrons, stripped them dry, but it also tapped into the D subshell and was pulling electrons from that D subshell. So your transition metals can lose not only their valence electrons, but can lose the electrons that are in their D subshell in redox reactions. And this is why manganese, when paired with oxygen, has a charge of +7. Now we can accurately compare +7 to +2. So it means that the overall charge of manganese over here is +2, and that means that it has gone from +7 to +2, which means it's getting more negative. So because it's getting more negative, it means it's being reduced, okay, because it's gaining electrons. Now, another thing I'm going to do for simplicity down the track is here the difference is +2 to +3. So because the charge only went up by 1, it means it lost 1 electron. Whereas here, the charge went from +7 to +2. So it means the charge has, it means the manganese was reduced by 5 electrons. And that is the first and second step. Is the first step, we need to identify whether there is indeed a redox reaction occurring. And then once we've done that, we need to split the reaction into its half reactions and determine whether it's being oxidized or reduced. Now, the next thing that we need to do is we need to make sure this equation is balanced. Now, there is a big disclaimer here. This part's very important. I want you to check to see if our two half reactions are balanced in terms of just number of atoms on the left and number of atoms on the right, but do not include oxygen and hydrogen. Do not include them. The reason for that is we're going to balance those in future steps, okay? So what we do is we have a look over here. So we've got iron 2+, so we've got iron on the left, iron on the right, so that is balanced. And here we've got 1 manganese on the left and we've got 1 manganese on the right. So that's balanced. Don't worry about charges and that yet, because again, that's going to happen down the road. Now, again, we do not worry about this oxygen. So for all intention purposes, these reactions here are balanced. So now we have a look at our hydrogens and our oxygens and see if they're balanced. So we can see here there are no hydrogens or oxygens on this first equation over here. So there is nothing to balance. So our first half reaction is A-OK. Our second one, we can see that, okay, do we have any hydrogens? No, but we do have oxygens. So we have 4 oxygens on the left. So to balance our oxygens over here, we must add 4 waters, 4 H2O on the right. So that balances out oxygen. So we have 4 oxygens on the left and we have 4 oxygens on the right. But we've got a bit of a further problem now because now we need to balance our hydrogens. So we can see that we have 8 hydrogens on the right-hand side, because remembering we have 4 lots of 2 hydrogens. So to balance that, we put 8 hydrogens on the left. So again, we have a quick check to make sure our oxygens and our hydrogens are balanced. So we've got 8 hydrogens on the left, 4 times 2, 8 hydrogens on the right, 4 oxygens on the left, 4 times 1, 4 oxygens on the right, 1 manganese on the left, and 1 manganese on the right. So we're balanced. Now, our next step is we multiply both half reactions by each other so that the number of electrons equal. Now, this step can be taught in a multitude of different ways. A lot of people will write the electrons into these half reactions here and say, you know, if it's being oxidized, the electrons are on the right. If it's being reduced, the electrons are on the left. The way I do it is a little bit simpler because we don't have to worry about putting our electrons into the formula. So remember on our previous steps, on the step 2, when I wrote how many electrons were being moved, and I said that's going to come in handy later. This is the step where it comes in handy. So we can see written up here that with our first reaction, we have 1 electron being moved. So 1 electron is being oxidized, but with our manganese oxide going to manganese, 5 electrons are being reduced. Now this raises some eyebrows because it's basically saying, where are those electrons coming from? So an example would be if I was to throw 1 pen at you. So we have iron 2+ going to iron 3+. So it's only losing 1 electron. So that's the same as me just throwing 1 pen. But somehow we look away, a reaction occurs, but you catch 5 pens. So how does that work? How can I only throw 1 pen, but you catch 5 pens? How does that work? The answer is there must be 5 of me. There must be 5 lots of me throwing 1 pen each so that I am losing 5 pens total and you are catching 5 pens total. So again, this is being balanced because the number of electrons on the left-hand side that are being lost or oxidized are the same as 5 electrons being reduced or gained. So what we do is, to make this equal, we multiply them by each other. So we cross multiply. So we multiply this equation by 5, and we multiply this equation by 1. So 1 Fe2 plus, that turns into 5 Fe2 plus. 1 Fe3 plus, that turns into 5 Fe3 plus. So our second half reaction, we multiply everything by 1, so nothing changes. So essentially by doing this step, we simultaneously added in the electrons, made them equal each other, and then cancelled them out all in one step. So it means there's less confusion, there's less worrying about adding all the electrons up and all that sort of stuff. This step is a lot easier. It's just make sure that the number of electrons that are lost up here are the same number of electrons that are gained down here. Now, the next thing I like to call the stair step, and this one is dirt easy, okay? What you have to do is 3 simple movements. 1, 2, 3. Now, the purpose of this step is to combine your 2 half reactions together again. So what this means is that you write out everything on the left-hand side. So you write everything here, you draw an arrow, and then you draw out everything on the right. So again, all you're doing is fusing your 2 halves to form a whole. So what we do is, we write out everything on the left. We'll go to... Now, our next step is to cancel out any identical elements or compounds. Now, this is again a common student trap. This is where students get tripped up. Is that they will often look at this reaction and go, oh, okay, we've got iron on the left, we've got iron on the right, they must cancel each other out. And the answer is no, they don't. Because have a look, they're not identical. Here, this iron is 2+. Whereas over here, our iron is 3+. So because they're at a different oxidation number, the different charge, they have a different number of electrons. It means they're not identical and we cannot cancel them out. So there is nothing here that we can cancel out. The next thing that we do is a little step that I like to add in. So this is basically our final product. This is finished, it's solved and balanced. But this is how you can check your redox to make sure you got it right every single time. So what you do is you add all the charges up. So we have a look at 5Fe2+. So iron 2+, we have 5 lots of 2+. It means the overall charge is +10. 8H+, so 8 lots of +1. So that is +8. And MnO4-, so we want the charge of the overall compound, which is -1, which means our total charge for our reactants is +17. Now we have a look at 5Fe3+. So 5 times 3 is +15. Mn2+, we only have 1 lot of manganese. So that is +2. And we have 4H2O. Now, water is neutral. It is always neutral, and it will be nothing but neutral. So again, 15 plus 2 is 17. So now we have a look. So we have +17 on the left, we have +17 on the right, and that means that we have a very happy redox equation. And that is how you solve a redox equation with our final self-check at the very end to make sure that you get the question right every single time. Okay, so this now concludes Module 7 Video 1. Thank you all very much for watching. I know it was a very full-on module, but I hope you sort of all took something away from it. If you could all please just complete the survey down the doobly-doo description bar thingy-doozer, that would be fantastic, as it's only a very short 4 questions, and that really helps me out a lot. It gives me a lot of feedback about these online videos, and it gives me a lot of opportunity to improve them as well. So any and all feedback you can give me, it really does help me out a lot. If you do have any questions, queries, or suggestions, feel free to send me an email at b.grant@griffith.edu.au. Thank you all very much for viewing. Keep up the hard work, and I'll see you next time.